In this example, we're told we have this container, this tank, that has two compartments in it, A and B, and they're closed. One is filled with air, so tank A is filled with air, and tank B is filled with fluid with a specific gravity equal to, it's a liquid filled with specific fluid with a specific gravity equal to 0.6, so that's this tank B. If atmospheric pressure is 101 kilopascals, absolute, that's the pressure out here in the atmosphere. And the pressure gauge reads 3.5 kilopascals gauge. That's this pressure gauge right here. Determine the manometer reading H. H is this distance here. So there are actually two manometers. We've got one manometer here. They're both U-tube manometers. This one has mercury as the working fluid. And there's a height difference here of about 3 centimeters. Then we go into this tank B, and that part of the manometer is filled with this liquid with specific gravity of 0.6. And then we have the second U-tube manometer here, and then in this one we have water as the working fluid, and that's the height difference there is H, which is what we're trying to find, and then we move into the tank A with air, and that pressure is given there. So to find the pressure here, what we're going to do is we're going to work through a couple of manometers and combine the results together. Okay, so let's first of all start with let's just put a couple of points here. Let's call this point 1 right here. Let's call that interface there point 2. Then we're going to call this interface here point 3, and then finally that interface there we're going to call point 4. Okay, it's just to help us with some notation. And also just to kind of make things a little easier, instead of putting the numbers in, I'm going to put some different distances here. So we're going to call this 3 centimeters L1. We'll call the 2 centimeters here, we'll call that L2. Of course, we already have H listed there, so we don't need to rename that one. Okay, so let's go ahead and start working our way around the manometer. So let's find the pressure at 2, starting with the pressure at 1. The pressure at 1 is just atmospheric because it's open to the atmosphere here, and that's just air. So the pressure at 2 will be the pressure at 1. It's the pressure we start with, and then we're moving up a distance of L1. We're moving from point 1, we can go over horizontally, it's the same pressure. We move up to point 2, a distance of L1, and that's in mercury. So we're going to remove some of the weight of the mercury, so this will just be specific gravity of mercury times the density of water times G times the distance L1. So that gives us the pressure at 2. Now, to find the pressure at 3, what we're going to do is we're going to start with the pressure at 2. So we're going to find the pressure at 3, starting at the pressure at 2. And we're going to move up a distance of L2. Now we're moving in this liquid with specific gravity of 0.6. So we're moving up a distance of L2 to get us to that point, and then another distance of H to get us to 0.3. So we're moving upwards, so we're subtracting some weight. So this is the specific gravity of this liquid. I'll just call it little l, just for the liquid, times the density of water. So this combination here gives me the density of that liquid, times G times distance of L2 plus little h. So that now gives me the pressure at 3. Now to find the pressure at 4, I'm going to start at the pressure at 3 and then add in the weight of this water over that distance h. So P4 will be P3 plus, now I'm moving just in water, and I'm moving a distance of h there. Okay, so I can then combine these together. I can take this P2, plug it into there, and then take that P3 and plug it into there, and combine everything together. So let me go ahead and do that, and I'll just write out all the I won't bore you with all the algebra. I'll just write the whole thing out. Get rid of that, parentheses. Okay, so that is the pressure at 4 in terms of the pressure at 1. And the pressure at 4, by the way, so the pressure at 4 is this pressure here. Okay, because remember this is air and the pressure is going to be constant. We don't have to worry about elevation differences when we're dealing with a gas. We're assuming this distance is not on the order of thousands of feet. So the pressure at 4 is going to be that pressure there. So we know this P4. And this is given as a gauge pressure. So P1, the pressure over here, that's just atmospheric. So in terms of gauge pressure, this is just going to be 0 gauge. This one is the 3.5 kilopascals gauge. Specific gravity of mercury, you can look that up. That's 13.6. The density of water is 1,000 kilograms per cubic meter. G, of course, is 9.81 meters per second squared. L1, just coming up to the picture here, is, let me fix that. That's going to be 0.03 meters. This specific gravity is 0.6. That was given right here. The L2 is this distance here. That's 2 centimeters, so that's 0.02 meters. And we have everything else. So we can solve this equation ultimately for h. That's what we're trying to find is the h here. So we can go through some algebra to work that all out. I'm not going to go through all that. It's just algebra. It's pretty straightforward. But I will give you the final result. When you work out all the numbers, the h comes out to be 1.9 meters. So this problem is a good example of using a couple of manometers. Basically, what we did is we just worked our way around from right to left. We started at point 1, found, we moved in one fluid. Here it's the mercury. Defined the pressure at 2. So that was this equation. And then we moved in a different fluid from point 2 to point 3. That's in this liquid. That was that relation. And then we finally moved in the third fluid, water, to go from 3 to 4. That's that equation. And we already knew the pressure at 4 here because it's given right there. This is a gas, so we don't have to worry about elevation differences there. And then it's just a matter of algebra. All right, we'll end it there.